chapter. We're going to talk a little more about chemical bonding. Going to brush the concept of polar covalent bonds. These will become important to us later in the semester. And we're going to do nomenclature. Nomenclature for both molecular and ionic compounds. Remember, after we finish chapter 4, we're up for our first exam. So we'll talk a little bit more about what happens after this. We're going to have a sample exam that shows up on Blackboard. You will do it and hand it in. And we will go over the sample exam, and the following week we will have the real exam. But more about that later. And we'll also talk about this guy just a little bit later. All right. We talked some time ago about compounds and the two basic types that they exist in. We said that there were molecular compounds and there were ionic compounds. They have more than one type of atom, and they're bonded together. They differ in the way that they're bonded together. In a molecular compound, this is methane gas. We'll see later this could also be called carbon tetrahydride, but nobody would ever call it that. But nonetheless, this is a molecular compound. The electrons between the carbons and the hydrogens are shared. They're shared in such a way that the carbon winds up with an octet of electrons around it, and each hydrogen has 2. That's a molecular compound. An ionic compound, however, is simply composed of ions, cations, and anions in an array. They're packed like this, and they form crystals or whatever. The electrons are totally transferred from one atom, that's the cation, to the anion, and they're held together by electrostatic forces. It's another example of an organic compound. We looked at nitrogen gas. We did its Lewis structure. It had a triple bond. Well, here's an example of an organic compound with a double bond. Again, these are covalent electrons, and they're shared. An array that you might see in something like sodium chloride would look like this. Again, we have sodium cations and chloride anions. These are packed together nice and tightly as they can get, and they form the crystalline structures. Now we talked about Lewis dot structures. Remember, the important thing about Lewis dot structures is that it's simply a bookkeeping method. Simply bookkeeping. It really doesn't matter how you draw your little dots as long as you follow the basic rules. Basic rules were that you put the element symbol in, you put 4 single electrons around it, and then if you have more, you pair them up. We showed how you could make an anion. That's a negatively charged ion. And how you could show this as a Lewis structure. This is chlorine. Chlorine is right here on the periodic table. It's in group 7. It has 7 valence electrons. 3 of these we show as pairs, and the last one just sits down here by itself. This is chlorine, the element, as you see it over here in the periodic table. If we want to make an anion, that means it has 1 extra electron. All we have to do is bring the electron in. We now have 8 electrons surrounding the chlorine, and it has a negative charge. This, we'll see, is the chloride anion. Any questions? The whole point of bringing in the extra electrons, remember, was to try to get to the electron configuration in group 8. Group 8 is our inert gases. When you have all the electrons paired around an atom, that makes it a very stable configuration. So whenever you form bonds, whenever you form ions, you're typically shooting to make an octet of electrons around the atom. We call this the octet rule. Now today we're going to look at nomenclature. And in order to do nomenclature of ionic compounds, it's essential to introduce the concept of polyatomic ions. A polyatomic ion is a group of atoms that are bonded together by covalent bonds. So typically, in fact, always, these are going to be nonmetals or semimetals in the ion itself. They're either going to have extra electrons or they're going to be missing one. So they'll be cationic or anionic. And we're going to combine these with simple metal ions to give complex ionic compounds. As an example here, I have strontium sulfate. Now strontium, over here in the periodic table, right there, Sr, it's in our second group, is going to form a dication, Sr2 plus. The sulfate anion that we've paired with it here looks like this. Has 1 sulfur, 4 oxygens, and a -2 charge. Now, because strontium is +2, sulfate is -2, this is a neutral compound, isn't it? Same number of charges for both. If you note, we have sulfur, which is a nonmetal, and oxygen, which is also a nonmetal. These are all bonded together, and they make this polyatomic ion. Actually, it looks something like this. Sulfur in the middle, 4 oxygens around, and we have 2 negative oxygens. This is an example of a polyatomic ion. Now, these are very, very common. That's why we have to do this exercise, so that we know what sulfate is, what carbonate is, what nitrate is, etc., etc. Those are all polyatomic ions. Once again, all of these bonds to the sulfur and oxygens are covalent. The complex has 2 extra electrons, so it's a dianion. And this is an example of the crystal here. We have strontium, and here's these little lumps of sulfate that fit in between, and they make the individual crystals. Now comes the scary part. There are lots of polyatomic ions, kind of like this. You actually need to know these, or at least some of these, many of these. And you're going to need to know them both for the quiz, which, by the way, is online right now, and you need to know it for the first exam. We're going to go through the ones that you really need to know. And as we work examples, please pay attention to the ions that we use, because those are the ones that we really do need to know for the quiz and for the exam. The quiz, just to bring it up again, is online. You have unlimited attempts at this quiz, so you can take this thing over and over and over again. It draws from a database of questions, so no 2 quizzes that you take will be the same. They'll all be different. But again, you can do it over and over again. Blackboard will keep your highest score. You must have this quiz finished before the first exam. Okay? Just so we know the rules. All right, so we're going to look at some of these guys. We're going to look at a strategy that exists that makes it a little bit easier to remember some of these things. We're looking here at oxygen-containing polyatomic ions. So, like sulfate, it had an oxygen in it. There's a bit of a pattern that these things follow. And it really does make it much easier to remember them. We start off with the parent. We looked at sulfate. Sulf is our root. And to show that it's a polyatomic ion, we add ATE. The parent in the group gets ATE as its end. Sulf is the prefix, ate as the suffix. Whenever you see ATE, you're looking at the parent compound. Now these are oxygen containing. If we add one more oxygen to this ion, we get something we will call a per something ate. Per as a prefix tells us there's one extra oxygen. If we had per sulfate, it would just be one more oxygen than we had in sulfate. If our prefix or suffix here is ite, ite, that simply means we have one less oxygen. Now with one less oxygen than our parent, again, our suffix is ite. Sulfite, for example. If we had two less oxygens, we would put a prefix of hypo and stick an ite on the end. So the things to remember, we do per, we do the parent, we do ite, we do hypoite. The nice thing about this is that when you deal with a family, these are all going to have exactly the same charge. So realistically, all you have to do is remember the parent. Remember what it is, how many oxygens it has, and then from that, you can go up and down and make the rest. They all are going to have the same charge. Any question on the concept? Well, let's look at a simple example. These are chlorine-containing ions. And this is our example because this works really well. Our parent here ends in ate. This is chlor. Chlor is our prefix. And ate means that this is the parent. Chlorate is the parent. It has a -1 charge. If we add one oxygen, we get perchlorate, still the same charge. If we take one away from the parent, ClO2, chlorite, ITE, again the same charge. Take two away, hypochlorite. Bleach, everybody uses bleach. Bleach is sodium hypochlorite, NaClO. Everyone see the pattern here. All you really have to do is remember, in this family, chlorate is our parent. It has a -1 charge, ClO3. Sulfurs, we talked about sulfate. We take one oxygen away from sulfate, we get sulfite, SO3. Again, they have the same charge. Now we saw what sulfate looked like. We have these oxygens out there. When you have oxygens dangling out, you can put a hydrogen on them. Hydrogen goes on as H+, so it will neutralize this, and you will form, this is hydrogen sulfate. That's this right here. We write it HSO4, and since we put a positive hydrogen on it, a +1, our charge drops from -2 down to -1. Just like we did hydrogen sulfate, we can do sulfite, stick a hydrogen on there, and go down to hydrogen sulfite. All we're doing is taking these negative oxygens and putting a hydrogen on. That neutralizes the charge, so it drops it by 1. As we do nomenclature in just a minute, please remember that these are separate words in the name. Hydrogen sulfate, 2 separate words, hydrogen sulfite. Phosphorus. Our parent here is going to be phosphate, PO4. This has 3 negative charges. If we have phosphite, we have 3 negative charges, but only 3 oxygens. So we drop the oxygen by 1 when we go to the ITE. Now with phosphate, we have 3 negative oxygens here. So we can put on 2 additional hydrogens. We get hydrogen phosphate if we put 1 on. If we put 2 on, we get dihydrogen phosphate. Once again, these are 2 separate words. I also stuck phosphite in here just to show you can do the same thing. We have 3 negatives, stick on 2 hydrogens, left with 1 negative here, dihydrogen phosphite. Now, carbon. Our parent here is carbonate. There is no carbonite. Carbonite was Star Wars. It's not real. Once again, we can stick a hydrogen on here and make hydrogen carbonate. Another common one that we'll see later on is acetate. Now we'll talk about this later on. It's not going to show up on your exam or whatever. Just know it exists. It's acetate. Acetic acid is vinegar. And this is the anion corresponding to vinegar after it loses a hydrogen. Cyanide is something we will see. That's a carbon-nitrogen triple bond with a single negative charge. Make sure you know that guy. Nitrogen. Nitrate is our parent. Nitrite, we take 1 oxygen away. Again, they have the same charge. And the only positively charged polyatomic we're going to talk about all semester is ammonium. NH3 is ammonia. That's common ammonia gas. If we put 1 more hydrogen on, we get a positive thing, NH4+, and that is called ammonium. Make sure you know that one. That one does show up on exams and quizzes. The only positive polyatomic we're going to deal with. Any questions? Now I do apologize for the fact that you have to remember these things. Okay, so work on it, practice. Again, the problems that we'll do, the problems that you do on the tutorials should reinforce this enough that you can remember these things. All right, let's look at where these things come from. Let's do this by making a Lewis structure for the chlorate anion. Now we remember chlorate, it's ATE, this is our parent, isn't it? It has a -1 charge. So let's go ahead and build this thing using a Lewis structure. Now, we talked about this last time. The way you're going to do this is find the atoms on the periodic table. You're going to figure out how many valence electrons they have. Put them together in a little ball. And then we're going to pair them up so they can form bonds. Only 2 electrons per bond. So, chlorine is here in group 7. It has 7 valence electrons, doesn't it? Oxygen is here in group 6. It has 6 valence electrons. We have 3 oxygens, chlorine in the middle. This is just what we're starting with. 7 electrons around the chlorine, 6 electrons around the oxygens. Now we look at this and say, oh my goodness, this is silly. We know darn well we can't have 3 electrons in a bond, can we? Nor do we really want these lone electrons just standing out there by themselves. So Lewis structure is just bookkeeping. Just bookkeeping. We want to pair things up whenever we can. So let's start off by taking the odd electron from here and here and just pairing it top and top, like this. Just like that. Wasn't that simple? Here, I can go back. And I can go forward. So now we're in good shape. Remember, we need 2 electrons to make a bond. 3 wouldn't work. 2 works fine. We can make a bond here. Share these 2 between these 2 atoms. Share these 2 here. But by gosh, we only have 1 here. That's a shame. However, remember this is the chlorate anion. Now what we have here so far is totally neutral. In order to make it the anion, we need to add 1 extra electron. If we do this, now we have 2 electrons between these 2 atoms, a negative charge on the whole thingy because we put 1 more in, and now we're ready to make our bonds. 2 electrons per bond, scooch them up. Here we have 8 electrons around our oxygens. All oxygens have 8 electrons, don't they? And our chlorine in the middle also has 8, 2, 4, 6, 8. Everybody has an octet. Everybody is happy. We'll take and we'll make our bonds into dashes. And this is what we would draw for the chlorate anion. Remember the dash. Whenever you see a dash between atoms, that tells you those are 2 electrons that are involved in a covalent bond. If we have 2 dashes, that's 4 electrons. 3 dashes would be 6. Every dash is 2 electrons in a covalent bond. Any questions? Now, chlorate here follows the octet rule very nicely. Everybody winds up with 8 electrons. Everybody has a happy face on. However, there are exceptions to the octet rule. And we're just going to look at these just so that you don't think that Lewis is always right. Okay? Just so that you see that there are exceptions, there are compounds where you don't have 8, sometimes more, sometimes less, and we're going to see quickly how we get to it. This is the compound SF4, sulfur tetrafluoride. This is its geometry. We have 2 fluorines up and down, they're called axial. We have 2 fluorines in an equatorial position and 1 lone pair of electrons. This is what it looks like as a model. The electrons come out here. Just to show that chemists do in fact have a sense of humor, somewhat, this is called a seesaw structure. Why is it a seesaw? Well, because it kind of is. This is the seesaw structure. Now let's see where our bonding comes from in SF4. In SF4, we have sulfur. It's going to be here in group 6, so it has 6 electrons. We have oxygen, which is in group 6 also. So, I'm sorry, fluorine here. That's fluoride, not oxygen. Fluorine is here in group 7. It has 7 electrons. So step 1, we're going to take our sulfur, put it in the middle, put 6 electrons around it, and then we're going to stuff 4 fluorines around it with 7 electrons each. One thing I want to point out before this goes away, sulfur is here in our 3rd period. So what we're going to talk about actually only applies to atoms in the 3rd period and below. First 2, none of this applies to, but 3rd and below can do this little trick that we're going to do. All right, so let's make this thing. We have a sulfur with its 6 electrons, and we have 4 fluorines with 7 each. Right? That's what we got. Now, as we look at this, we feel very comfortable because we have 2 electrons here. Hey, that's a bond, isn't it? We have 2 electrons here. That's a bond. But oh my goodness, here we have 3 and 3. Now, what in the world are we going to do with those? Only 2 can go in a bond, right? Well, this is a very simple trick. There's no other place we can put them. Not like with chlorate, we can't move it anywhere else. Everything is full. So what we're going to do here is we're just going to identify 2 electrons, say like these 2, and I'm going to go put them in storage. I'm going to go put them in the next room somewhere. So they're gone. Now that we did that, if you look at what we're left with, again, here's what we started with. Going to just take these 2 and get rid of them for right now. By gosh, we can make a bond here, a bond here, a bond here, a bond here, and everybody would have 8. Everybody would be happy, wouldn't they? So let's do that. But we can't forget that in the next room here, we have these 2 electrons that we have to put back. Where do they go? Well, they must go back on the sulfur. So all the fluorines have 8, but our sulfur now has 10. How can it do that? That's because, like I said, it lives in the 3rd period. 3rd period and below, you can put up to 14 electrons around the central atom. and we stick them in just like this. This is called valence expansion. If we go anything, third period and down, we can do valence expansion. So this is the first exception to the octet rule. Again, if you're in the third period and below, you can put 10, 12, 14 electrons around your central atom. We won't do that in this course. We're going to restrict ourselves to the top two. Once again, this is what it looks like. The extra pair of electrons, if you were interested, is actually in a hybridized orbital called an sp3d orbital. Remember, in the third period and below, we can have d orbitals. And that's the place that you're putting these extra electrons.
Oh, can you tell me where did you get the extra electrons? I'm sort of missing that.
Where did it come from? Well, when we put our structure together,
Right.
let's go all the way back. This is all the electrons. Here we go. Sulfur has 6. Every fluorine has 7. So that's what we're starting with. In order to make our bonds, we have to somehow get rid of 2 of these just for a minute, so we can make nice, happy bonds between everybody. Once we've done that, we simply have to put them back. And here's our final compound. 10 electrons around the sulfur. All right, so sulfur had too many. It doesn't always, but it can. Go ahead and I will hush for a second. Draw the Lewis structure for BH3. Boron is in our third period. It has 3 valence electrons. Hydrogen is in the first period. It has 1 valence electron. So to draw our structure, we put a B, and we put 3 dots around it. 3 separate dots, right? We have 3 hydrogens. They each have 1 little dot associated with them. And you would get, here's our boron with its 3, and 3 hydrogens. All right, well, we need 2 electrons to form a bond, don't we? My gosh, we have 2 electrons, 2 electrons, and 2 electrons. So we can do that. Scooch them up, form our bonds. However, when you look at this, our boron is sitting there in the middle. Instead of an octet, it only has 6. And there is no way in this world that you can give it 8. There is no way you can do that. So sulfur had too many, boron has too few. This is BH3. Later on in life here, we will call this a Lewis acid. A Lewis acid is an electron acceptor. Why would boron be an electron acceptor? Because it only has 6 and it dearly wants 8. So it will accept electrons into this giant hole and form bonds with things. So Lewis acid electron acceptor. That's chapter 8. Any questions?
Can you put that in any order, as long as you have the same amount of electrons? 'Cause you got yours, your order is a little bit different from mine, so I still have the same though. So does it matter? See, I got the 2 H's and
No,
the
you're
H
good.
right there.
Yep,
So-
you're good. Remember, this is bookkeeping. Doesn't matter how you arrange them at all. Doesn't matter. As long as you put 4 singles, then pair them up, and make bonds with only 2 electrons each. All right. Let's go and talk just a little bit more about ionic compounds. And then we're going to talk about naming them.
I'm sorry, I have to take this one.
An ionic compound, we said, occurs when a metal ion, in this case sodium, transfers an electron from itself to another atom that makes a positive ion and a negative ion. These have names. Please remember the names. A positively charged ion is called a cation. Cat, like a kitty cat. A negatively charged ion is called an anion. So here we have cations and anions. This is the sodium cation plus 1 and the chloride anion minus 1. Now, when you make a crystal or a structure of sodium and chloride ions, they tend to line up, as we've shown here. If you notice, this is a cube. It's a very nice, happy cube. If you look at the detail of a crystal of sodium chloride, you'll see it has really sharp little edges and is basically cubic. You look at table salt under a microscope. They're all little tiny cubes. That's because the simplest way to pack these anions and cations together generates this cubic structure, perpendicular edges. Now I said that sodium was going to give up its 1 electron to chlorine, right? How do we know that? Well, we know that because we look at our periodic table. Remember we talked about our groups here, 1 to 8. And I said that was a good thing to use those as our group numbers. Turns out that the metal ions that are in group 1 form a positive ion with a +1 charge. Metal ions in group 2 are +2. The metal ions in 3 are +3, and the metals here in 4 are +4. So the group number tells you the charge on the metal ion. In terms of anions, the anions are going to be at this end of the periodic table. In group 5, we're going to have -3, group 6, -2, and group 7, -1. Think about it logically in terms of an octet. If you're in group 7, you need 1 electron to get over to 8, don't you? So that's a -1. If you're in group 6, you need 2 electrons. In group 5, you need 3 electrons. So that's the way the charges work relative to the periodic table. Now when you put together an ionic compound, the compound that you write, the total compound, must be neutral. This concept has a name. It's called the principle of charge balance. And all in the world it says is you must have the same number of pluses as you do minuses. So here we have a compound made up of magnesium and sulfur. Magnesium is in group 2, so it'll be a +2. Sulfur is in group, I can't quite get there, it is 6. So it will be a -2. We put these together, a +2 and a -2, our net charge is 0. Sodium group 1, bromine group 7, +1, -1. Again, it's neutral. If we were to pair sodium, which is group 1, with sulfur, which is group 6, this is going to be a -2, so we need 2 of these guys. 2 pluses, 2 minuses. Again, we're neutral. And here, just the opposite, magnesium +2. That's our second period. Bromine is group 7. That's a -1. It takes 2 of those. Once again, we're at 0. So that's the principle of charge balance. Really a simple concept. It must wind up as 0. Next, when we're building, or showing at least, an ionic compound, the formula that we write must have the simplest whole number ratio of the atoms. So here we have magnesium +2, sulfur -2. It's neutral. We would write this compound simply as Mgs. If we had written it as Mg2S2, that's wrong. The simplest whole number ratio is 1:1. Sodium bromide, that's neutral. We write it NaBr. Here we have 2 sodiums for every sulfide. We're going to use our subscript to indicate that we have 2 sodiums, Na2, for every sulfur. And likewise here for magnesium and bromine. For every magnesium, we must have 2 bromines. And it would be written this way. The 2 tells us 2 bromines for every magnesium. Any questions? When we make a compound that's ionic, this is actually referred to not as a molecule. Molecules are reserved for molecular compounds. Now, everybody's going to call sodium chloride a molecule. You are. But legally, it's called a formula unit. And again, the formula unit is the lowest whole number ratio of the atoms in the compound. Sodium chloride, 1 sodium, 1 chlorine, HF, H2O, water, 2 hydrogens to 1 oxygen. Now here's our polyatomic. Sulfate has a charge of -2, doesn't it? We remember that. We hope we do. Do remember that. Potassium is here in group 1. So it is a +1 ion. You need 2 potassiums for every sulfate. And as you read this formula, you should tell yourself 2 potassiums, 1 sulfur, 4 oxygens. Any questions? All right, well, let's build a couple simple compounds. Go ahead and write the formula for a compound made of magnesium and chlorine. Step one, you have to find them on the periodic table, don't you? Magnesium is here in group 2, right there. So it'll form a +2, won't it? Chlorine is here in group 7. It'll form a -1. Magnesium is +2. Chlorine is -1. Therefore, in order to get our neutral compound, what do we need? For every magnesium, we need 2 chlorines. And we would simply write it MgCl2. Now that's simple. Let's go ahead and do one that's a little more interesting. Aluminum and oxygen. Aluminum is here in group 3. So what's its charge? +3. Oxygen is here in group 6. So what's its charge? -2. +3, -2. Now, your job is to put these together so we wind up with a neutral compound. There's a little simple trick you can do. Here I'm just going to write aluminum +3 and oxygen -2. Okay? That's what we're starting with, right? Now I'm going to write them again down here. And I'm going to do a little symmetry swap. I'm going to take the 3 from here, move it to the oxygen, the 2 from here, move it to the aluminum, and that's our compound. Think about it. Aluminum is +3. This is 6 positives, isn't it? Oxygen is -2. This is 6 negatives. Our little simple symmetry swap will always work. Take the charge on the first one, put it as a subscript on the second. Charge on the second, put it as a subscript on the first. It always works. And once again, check yourself. We have aluminum, which is a +3. We have 2 of them. That's 6 positives. Oxygen is -2. We have 3. That's 6 negatives. Any questions? Let's do beryllium and selenium. Beryllium is this little guy here in group 2. So what's its charge? +2. Selenium is here, is hiding down here underneath sulfur. It's group 6, so it will be a -2. Now, let's go ahead and write our simple structure here. If we did what I just said, and that is to write BES and take our charges and put there, we would get Be2S2, wouldn't we? But we know that's wrong, because that's not the simplest whole number ratio, is it? So this is where you have to be careful doing your crisscross. This, of course, is simply BESE. Make sure you always wind up with the lowest whole number ratio. Any questions? Well, isn't it about time that we went ahead and just gave these little guys real names? Yeah. I mean, calling it BESE is kind of demeaning. Let's give it a real name. When we name ionic compounds, remember these contain a cation and an anion, right? In our formula, the cation always comes first. In our name, the cation always comes first. So we're going to write the cation just as the name of the element. Magnesium, whatever. That's our first word, separate word. Now for our second word, we're going to do the anion. Here. To show that it's an anion, we want to add the suffix IDE. We're going to add it to our root name. So chlorine, for example, would be chlor. If it's the anion, it would be chloride. Now, naming these things is going to be really simple for you because we don't use multipliers at all. But let's see what this means. Here we have a compound made up of magnesium and bromine, right? The first word in our name is simply going to be magnesium. Now the root for bromine is going to be brome. We're going to add our IDE and make this bromide. This is magnesium bromide. Our first element here is sodium. Our second element, chlorine. The root is chlor. Therefore, we're going to write the anion as chloride. Go ahead and write these two before I say them. This is potassium, this is beryllium. Potassium and sulfide. Beryllium and bromide. Very simple to name. Any questions? All right, let me hush for a second. And you do this set. Our first compound here, our first element is Ca. That is here in our second group. That's calcium, isn't it? We have it paired with two bromines. This is calcium bromide. We did this one as a problem. Al is aluminum. O, of course, is oxygen. This is simply aluminum oxide. Li is lithium. S is sulfur. So this is simply lithium sulfide. Ca once again is calcium. O is oxygen, calcium oxide. Now this guy, we're going to name it incorrectly. I told you that, point blank. Ni is right there, it's nickel. So we look at this and say, well, this is nickel, this is chlorine. I'm going to write nickel chloride. But I'd be wrong. Now, why is that? The elements that we've been using so far are in the groups 1 through 8. We've kind of skipped these guys in the middle here, haven't we? Remember the guys in the middle? These are called transition metals. They fall outside of our normal groups. And they can be a little bit peculiar. In terms of charge on the ions, quite often a transition metal can have several different charges. So the nickel here could be a +1, or it could be a +2. If you simply said nickel chloride, you wouldn't know if this was a 1 or a 2. In order to fix that, and we'll show this a little bit later, we have to write it this way. We put the charge, which is 2, after the element in parenthesis in Roman numerals. So this is most properly nickel 2 chloride. Now again, we'll talk about that in a bit more detail. Any questions? Yeah.
Why is it that the aluminum oxide was not the same like nickel, because aluminum is part of the...
No, aluminum is here in group 3. Once you make it to group 3, these guys here are the transition metals. Groups 1 through 8 are still good.
Is it because aluminum is a transition?
Nope, it's not. Transition metals are these guys in between, from here to here. All right, let's work backwards. Now remember I said you were happy with yourself that you didn't have to write multipliers. However, that means that if you have to work backwards, you don't get multipliers to help you, do you? So, let's do our first one here, and then you can do the rest. Calcium nitride, write our formula. Well, calcium we all know is Ca. It's right there. It's group 2. So it's going to be a +2 ion, right? Nitride, nitrogen, I can see it here, right there. That's in group 5. Now if it's in group 5, what kind of an anion will it be? It'll be a -3. So we have a +2 and a -3. Do your little crisscross. Calcium is +2, nitrogen is -3. Going to simply cross our 2 down to our nitrogen, the 3 down to our calcium, and we get Ca3N2. Calcium is +2, so we have 6 positives. Nitrogen is -3, we have 6 negatives. Go ahead and do the rest of these, and then we'll check them. On your exam, you'll get a periodic table. It'll look pretty much like this one, except small. It will not be colored. So you're not allowed to bring your own. You have to use the black and white version of this guy.
Does it come with the numbers?
Oh yeah, it comes with all the numbers and everything.
Thank you.
Just no colors. All right, magnesium. Magnesium is our second group. It'll be a +2. Oxygen is in our fourth group. It will be, our sixth. It will be a -2. We have a +2 and a -2. That's easy. This is simply MgO. Lithium is here in group 1. It will be a +1. Iodine is somewhere over here. It will be a -1 because it's in group 7. So we have a +1 and a -1. We simply put them together and spell Lil. Barium is here in our second group. There it is. It is a +2. Phosphorus. Phosphorus is here below nitrogen. So that's our fifth group. Phosphide will be a -3. So once again, we have a +2 and a -3. Simply cross your numbers. 3 bariums, 2 phosphorus, and finally, beryllium fluoride. Beryllium. Beryllium is there in our second group, so it's a +2. Fluorine is over here in our 7th group, somewhere. So it is a -1. +2, -1. We need 2 fluorines for every beryllium. BeF2. Any questions? Pretty simple. Once you understand the basics of the nomenclature. Now let's just take it up again one more notch. Remember our friendly group of polyatomics. These also show up in our ionic compounds. So go ahead and write a formula or write names for these compounds. Now here you can look back at your table and figure out what's what. On the exam you can't. But these are simple ones that you should know. First word in our name is going to be calcium, isn't it? What is CO3 minus? Look at your table. That's carbonate. And we simply write this as calcium carbonate. Now the only positive cationic, the only positive polyatomic ion that we are going to talk about is in H4. Look at this in your table. This is ammonium. So our first word is ammonium. It's paired with a chlorine, so this is ammonium chloride. Our first element is sodium. SO4 is what? We've done this one several times now. SO4 is sulfate. If we take one oxygen off sulfate, what do we get? Sulfite. So this is simply lithium sulfite. And finally, we have three words in our name here. Potassium is going to be the first. Hydrogen will be our second. And what is PO4? It's phosphate. Potassium, hydrogen, phosphate. Let's do these backwards. Now, at least one of these might be different than is shown on your sheet, because I changed it today. So just use what I have on the board here. Lithium, that's going to be an Li, we know that. Now we have perchlorate. So this has one more oxygen than the parent. The parent is chlorate, ClO3. So this must be ClO4. Remember we did the Lewis structure for chlorate. We had one minus charge. So this is also a minus one charge. Simply LiClO4. Lithium perchlorate. Barium is going to be Ba. This is sulfite. Our parent we know is sulfate. That's SO4. It has two negative charges. Sulfite will also have two negative charges, but one less oxygen. So that's going to be SO3. Plus 2 minus 2, and it just looks like that. Aluminum chlorate. Now aluminum is a +3, isn't it? What's the charge on chlorate? We've already said that. We did it in class. It's a -1. So how many chlorates do we need to balance our aluminum? +3 -1, we need 3 of them, don't we? How do we show that? We're going to take chlorate in parentheses and put a 3 down here. 1 aluminum for 3 chlorates. Silver nitrate. Now silver is Ag. Somebody's going to look at that and tell me that's a transition metal. But silver is one of the reliable transition metals. It is always +1. It's always +1. It is so reliably +1 that we don't need to put down the oxidation number. Silver is an exception. We can just write Ag, nitrate is NO3, don't need to put our charge. There are a couple exceptions, but silver and gold are the good ones. Finally, barium cyanide. Barium is B8. It's over here, so it's a +2. Now remember, cyanide was carbon triply bonded to a nitrogen, and it had a -1 charge. So if this is +2, how many -1s? 2 of them. So we have to put our cyanide in parentheses. Barium, cyanide, we show our 2 minuses and 2 pluses. Any question? How in the world are you supposed to learn this? It just takes a little bit of practice. The ones that we've talked about in class are the ones you need to remember. Okay? Well, let's do one more exercise here. Quickly name these guys. Pb is lead, Fe is iron. In our first compound, we have a lead and an oxygen, don't we? So what would we call that? Lead oxide. PbO2, lead and an oxygen. Well, that's lead oxide too. Iron and oxygen. Iron oxide. Iron oxide. Iron oxide. This is what happens to typical transition metals. Lead is somewhere. Lead is somewhere. And iron is somewhere else. It's hard to see this far. These can have variable charges on them. And so just like the nickel we looked at earlier, we're going to have to put the charge. Now we're going to address a concept here called oxidation number. Really for the purposes of the course here, oxidation number is going to be the same as charge. If you go on to real chemistry, you'll look at oxidation number in a slightly different way. But these differ because of their oxidation number. Now, what's oxidation number? You look at the element in the periodic table, and you ask if the element you're working with has more or fewer electrons. That's the same thing as charge, isn't it? So, if we're dealing with a simple compound here, magnesium and bromine. The charge on the magnesium is +2. Charge on the bromine is -1. In terms of oxidation numbers, we would simply say oxidation of magnesium is +2, bromine is -1. The same as the charge, just a different terminology. Lithium phosphide, +1 and -3. The oxidation numbers are +1 and -3. Now for simple ionic compounds, this is really easy to do. there are lots of exceptions that show up, and so there are rules to describe this. Here's a set of rules that you really don't have to know. When you're dealing with an element by itself, it's always 0. Group 1 is always +1, group 2 are always +2, fluorine is always -1, oxygen is going to be -2, halogens -1, blah, blah, blah. What do you need to know? What you need to know, simply, it doesn't show up on this projector, but there is a yellow box around this right here. What I want you to remember is that when you see an oxygen, you think -2. When you see a halogen, that's something in group 7, you think -1. That's what you need to know. Now let's see how this works. Here's our PBO. We know that oxygen is going to be a -2. If this compound is neutral, that means the lead must be +2, right? So how do we write the name? Well, the oxidation number is 2. I guess we write the name in the next slide, I'm sorry. PbO2. Here we have 2 oxygens. Each one is going to be a -2. So that's 4 negatives. We need 4 positives here. So that's how you can use the oxygens to simply tell what the charge is on our metal. In this case, sulfate, we know that sulfate is always -2. If sulfate is always -2, that means the iron must be +2. And here we have oxygen. This is going to be 6 negatives, right? To make this neutral, we must have 6 positives, so the iron must be a +3. Now, like I said, back with nickel, the way we write this, the way we show this, is to use the charge or the oxidation number in Roman numerals. So for our PbO2, this is going to be a -4, so the lead must be a +4. We would write lead 4 oxide. No space here. There's a tutorial that deals with this. If you put a space in, you get it wrong. Okay? Lead 4 oxide. This oxygen is -2. That means the lead must be +2. So we would write lead 2 oxide. Carbonate, we know, is -2. That means the iron must be +2. So we write iron 2 carbonate. And finally, bromide is going to be -1. So we have 3 negative charges. That means that this iron must be a +3. Iron 3 bromide. Any questions? Well, like I said, there are 3 tutorials that apply to this chapter. Let's look at one of them. In this one, you are simply given a formula, and you have a blank here to write the name. Spelling counts. First thing we do is we look and we see where barium is on the periodic table. Barium is right down there. It's in group 2. So it's not a transition metal. If it's not a transition metal, you don't have to put the charge, do you? So our first word is simply going to be barium. The anion here is iodine, so we would write iodide. And this would be barium iodide. And by gosh, I got it right. CUI. Step 1, is it a transition metal? Where does copper live? You can barely see it, but I think it's living about right there. It's a transition metal, so we have to put the oxidation number in. Now what will it be? Iodide. The halogen is going to be -1, isn't it? So that means this copper must be +1. So we would write copper 1 iodide. Remember, no space. Copper 1 iodide. One more. What is ClO? ClO3 is chlorate, isn't it? That's our parent. ClO2 is chlorite. And ClO is hypochlorite. And it has a -1 charge. We have 3 -1s. Iron, of course, is a transition metal, right there. So we have 3 -1s. We must have a +3 on our iron. We would call it iron 3 hypochlorite. Any questions? Do the tutorial. Not hard. It'll get you 5 points on this exam. And actually do it a lot, because there will be naming on the exam. And you know, it's just good practice. That's why I wrote these things, because they're good practice.
Can I ask you a question?
Sure.
You wrote the hypochlorite, okay, when you said we do
Hypochlorite.
hypo, it's where you take away 2
2 oxygen.
oxygens.
So our parent is ClO3.
Right, that's.
Take
cool.
away 1 is chlorite.
Oh, okay.
Take away 2 is hypochlorite. All right, molecular compounds. Molecular compounds are actually simple now that we've gone through all this nonsense. The only problem here is we're going to use multipliers. So how do we count in chemistry? We count monoди, tri, tetra, penta, hexa, hepta, octa, nona, and deca. You probably only need to know the first 5 or 6, but they're pretty obvious. I think everybody can do those. We're going to do the same thing. We're going to name the element, and then we're going to put what's bonded to it with an IDE, and we're going to use multipliers if we have to. The rules on multipliers: for our first element, if there's only 1, you don't use mono. For the first element, if there were 2 or more, then you would use the appropriate multiplier. For the second element, you always use a multiplier. So that's all you have to remember. Carbon with 4 chlorines. What are we going to name this? It's a molecular compound. They're both nonmetals. Our first word is simply going to be our first element, and that is carbon. We're not going to use mono, because we don't use a multiplier if there's only one of the first element. Now our second is going to be chloride, isn't it? How many do we have? We have 4. And how do we say 4 in chemistry? We say tetra. Carbon tetrachloride. Carbon tetrachloride, interesting compound. It's a marvelous, marvelous solvent. Back in the old days, machine shops and whatever, auto shops, would have big barrels of carbon tetrachloride. And you went in and you had a carburetor that was gunked up. They would take your carburetor, swish it around in there, gets all the gunk out, works beautifully. Unfortunately, carbon tetrachloride is a carcinogen, so we don't do that anymore. Back in the old days, things were so much easier. 1 sulfur, 2 oxygens. What's our first word? Sulfur, and we're not going to use a mono, are we?
Dioxide.
We have 2 oxygens. How do we say 2? Di. Sulfur dioxide. When you burn sulfur in air, you form sulfur dioxide. It's actually a fairly toxic compound. Very, very irritating. As soon as it hits water, it forms sulfurous acid. A very strong acid, and it's not nice. 2 nitrogens, 1 oxygen. Well, here we have 2 of our first element, don't we? So we have to say that. You're going to say that by saying dinitrogen. Our second word, we have 1 oxygen. Remember, the second element always gets a multiplier.
Mono.
So this is monoxide. You note that we kind of dropped one of the O's. That's because too many O's in a line, it's just hard to say. Do one more here. Into O5. Now I will tell you on the last 100 exam, into O5 was on the exam. You had to give me a name. Okay? So what is it? We have 2 nitrogens. How do we say that? Dinitrogen. We have 5 oxygens. How do we say 5? Pent. Right. So this is dinitrogen pentoxide. Again, we drop the A here because, again, too many vowels. Now, if I was grading something and you put in the AO, do you think I would care? No. I'd be really happy that you got that close. But you drop it. Pentoxide. All right, let's go ahead and just name some guys. Just jot these down quickly. Remember, use multipliers for the second atom. If you only have 1 of the first, you don't use mono. Our first one, our first word is simply carbon. We have 2 oxygens. We say di for 2. This is carbon dioxide. Our second one, we have 2 hydrogens. So we're going to need a di in front of that. That's simply dihydrogen. We have 1 sulfur, so it's monosulfide. Silicon, just going to say silicon. We have 4 hydrogens, so that's a tetra. This is silicon tetrahydride. 1 sulfur, so our first word is sulfur. 3 is a tri, so this is a trioxide. And finally, we have nitrogen. As our first word, we have 3 chlorines. This is going to be nitrogen trichloride. Let's just make them a little more interesting. Go ahead and write these down. We have 4 phosphorus atoms. So that's going to be a tetraphosphorus, isn't it? We have 6 sulfurs, so that's a hexasulfide. We have 2 iodines, so it's a diiodine. And we have 7 oxygens. What's 7? Hept. This is diiodine heptoxide. Again, this is another one where we have the AO. We just dropped the A. 1 oxygen. 2 fluorines. Oxygen, difluoride. 1 carbon, 4 hydrogens. Carbon, tetrahydride. This is methane, natural gas. And finally, 4 sulfurs. That's a tetra, isn't it? Tetrasulfur, dinitride. And to wind up the set, let's just do 1 set backwards. Write these formulas. Our first one, we have nitrogen triiodide. That's 1 nitrogen and 3 iodines in I3. Nitrogen triiodide is a very, very sensitive contact explosive. We'll see a video of this in a little bit. Once you make the stuff, let it dry, you literally touch it. Just barely touch it, it explodes. Amazing. Diphosphorus pentoxide, that's 2 phosphorus, 5 oxygens. Oops. 1 sulfur, 3 chlorines. Nitrogen monoxide, that's 1 nitrogen, 1 oxygen. Just say no. And finally, hydrogen monochloride, so we have a hydrogen, 1 chlorine. We will refer to this as hydrochloric acid as we get later into the course. Any questions? Well, like I said, there are 2 more tutorials. Let's take a look. Here we are given a name, a formula, and we have to write the name. Remember to make sure you do separate words and you spell them correctly. We have 2 nitrogens, so that is dinitrogen, right? 3 oxygens, trioxide. NS. Kind of like NO except with an S. This is going to be nitrogen as our first word, no multiplier. And we're going to have a monosulfide. Let's work this backwards. Sulfur tetrabromide. Now, on the tutorials, when you're entering formulas, you obviously can't do superscripts or whatever, right? You can't. So, you're just going to write them out like this. Write your numbers in the same line as the other, no spaces. Just write it all out. We're going to have a sulfur, and we're going to have 4 bromines. So that's SBr4. You should write it like that. Next one. This is an ionic compound, sodium phosphate. Now, you have to think. What's the charge on sodium? It's +1, group 1, right there. What's the charge on phosphate? Right now you can look at your table. Phosphate, remember, was our -3. That's our -3 parent. So we need 3 sodiums for every phosphate. Phosphate is PO4. So we would write 3 sodiums, that's Na3, PO4. Na3, PO4. No space, all on the same line. Any questions? 3 tutorials, 15 total points, lots of practice. All right, in your set of slides, the next section has to do with dipoles. Your book covers dipoles at this point. I'm not going to, though, because we're going to cover them in much more depth in Chapter 8. So let's go ahead and skip over the dipole slides. They won't be on the exam or the quiz. And let's just look at some simple exam questions from past years. Question 1. Here we have sulfur 32, and it's a dianion. How many protons are in there? Now, if you've done the proton, neutron, electron tutorial, this should be trivial. What you do is look at your periodic table. You can find sulfur. Now, here's our sulfur. Let's write the atomic symbol, just to show that we can. Going to start off with an S. S for sulfur. Remember, as a subscript here, we put the atomic number. And as a superscript, this is called sulfur 32. That's the mass number. So the superscript is simply 32. Now remember, for an atomic symbol, this is what? The sum of protons and neutrons, right? And what is this? The atomic number is simply the number of protons. Here I put the -2 just to be good. Atomic number is the same thing as the number of protons. We have 16 protons, 16 neutrons, and 18, 2 extra, electrons. Straight out of the tutorial, protons, electrons, and neutrons. This was a naming question. These are all molecular substances. Quickly jot down their names. Real test questions here. NO. Don't use mono here. This is simply nitrogen. And we have monoxide. 1 silicon, 4 chlorines. Silicon, tetrafluoride. 2 phosphorus, 5 oxygens. I have to stick our dye in. This is a diphosphorus. Pent oxide. And finally, 1 carbon, 2 oxygens, carbon dioxide. On the exam, I also put this set in for going backwards. These are all ionic compounds. Remember, with an ionic compound, how do you know if it's ionic? It has a metal. If it has a metal, it's ionic. This is cesium, Cs. What's SO4? Sulfate. Mg is magnesium. What is Cn? That's our polyatomic ion. What is it? Everybody's favorite poison, cyanide. Potassium, what's NO3? It's the parent for the nitrogen compounds. It is nitrate. Calcium. Now, if phosphate is PO4, what's PO3? Phosphite. And finally, here we have 3 words. The first one is sodium, the second one is hydrogen. And what's SO3? sulfate is SO4,
So,
SO3 is sulfite. 3 words. Please practice these tutorials. Again, this will be on the exam. It is on the quiz. Make sure that you can do these things. Please. All right, I'd like to end up the chapter here talking a little bit about the geometry of molecular compounds. Now, ionic compounds just kind of stick together because they're pluses and minuses. Molecular compounds, however, have a defined geometry in space. Predicting that turns out to be relatively easy. A molecular compound will have a fixed ratio. Every methane will have 1 carbon, 4 hydrogens, and they're always arranged like this. This is called a tetrahedron. A tetrahedron is one of these shapes they don't teach you in kindergarten. They should. But all of these bonds are equal length, and the carbon is suspended equally between all of these guys. Bond angles are 109. It's a very, very common shape in nature.
what is it called again?
Called a tetrahedron.
Tetrahedron.
Tetrahedron. We'll see it in just a second. So again, this is our thing. We have a carbon and we have 4 hydrogens. The way we predict the geometry is simply to look at our central atom. So here, and we ask how many things are around it. What a molecule will do is it will take these pairs of electrons and put them as far apart as they possibly can from each other. That's because they're negative. They want to be as far apart as they can. So, if we started off with a central atom at this point, and we had 2 things attached, the way you can make them as far apart as possible is to make a linear arrangement. There's your atom in the middle, and we have these 2 in a straight line. Now what I'm going to do in this little movie is add orbitals one at a time. When we add the first one, this is our straight line. When we add the next one, this is a planar triangle. If we add our 4th one, this is our tetrahedron. Our 5th one gets a little more complicated. We have 120s here, these are vertical. And finally, we add our 6th, we have 4 around the middle, and 2 up and down. Again, we're going to deal specifically with 1, 2, and 3 in this course. So, adding one, adding another to make tetrahedron. So let's look at these. If we have a central atom and 2 things attached, our geometry is going to be like this, and it's going to be linear. If we have 3 things around our central atom, these are going to be in an triangle. Equilateral? I'm having trouble saying that. That's going to be in a triangle where everything is equal. 120-degree bond angles. And if we have 4 things around it, we have tetrahedral. Again, in a tetrahedron, so tetrahedral geometry, all the angles are the same, they're 109, all the distances are the same, and the central atom is lifted up a bit off of the bottom plane. This is what they look like. Again, straight line, triangle, And here's our tetrahedron. You can see our central atom is simply lifted up off this bottom plane. Now, how do we figure out what the geometry is going to be? What you're going to do is do a Lewis structure for a compound. And then simply count how many things you have around it. So let's do this for ammonia. Ammonia is NH3. We did this in class. Nitrogen is in group 5, so we have 5 electrons around it. Hydrogen is group 1. We have 1 electron around each. We pair them up, and our Lewis structure looked like that. Now, we look at this and say, how many things do we have around this nitrogen? Well, we have 1, 2, 3, and our lone pair of electrons here counts, that's 4. So we have 4 things around it. When you have 4 things around a central atom, what's our geometry? It's tetrahedral. Now, as we look at this, we can't really see these electrons, but they're there. So this looks like it's trigonal pyramidal, like a little pyramid here, but it's really the bottom part and this of a tetrahedron. When you add up the number of things around it, this is also called the steric number. The number of bonds and lone pairs. Nitrogen would look like this. Again, because it's only the bottom part of our tetrahedron, we call it a trigonal pyramidal, but we know if we include the electron pair, it is tetrahedral. Now, the one that's going to be important to you when we hit chapter 8-ish is water. So let's do this exercise with water. First of all, draw the Lewis structure. Oxygen is in the middle. It has 6 electrons. We have 2 hydrogens, 1 electron each, and they're going to pair up to make 2 bonds. When we're done, this is what we get. Now remember, it doesn't matter how you draw the thing. You can draw it at right angles, doesn't matter. As long as you have 2 hydrogens and 2 unshared pairs. So, what's our steric number? Well, we have 1, 2, 3, 4 things around it. Our steric number is 4. So what's our basic geometry? When you have 4 things, what is it? It's a tetrahedron. Now these 2 we see, these 2 we can't see, but they're there, and all together they make the tetrahedron. So it's this part of the tetrahedron we're seeing. And the geometry here we refer to as bent. Bent. Turns out that the reason that water is such an amazing solvent, and the reason that water is essential for life as we know it, all comes down to the fact that it has this bent geometry. If it didn't have the bent geometry, it wouldn't work. It's amazing. Again, we talk about this again in chapter 8. Just to complete the set for tetrahedra, if we have 4 real things around, that's like methane, a full tetrahedron, if we have three things around, trigonopyramidal looks like this, and only two, that's our bent, and that's water. Now there might be a question about this